Welcome to part 2 of nuclear physics. Here we're going to be looking at binding energy and mass defect, which is arguably the most famous equation in all of science, particularly physics, E equals mc squared. And we're going to see why it should probably be E equals delta mc squared if we want to be technical. So we're going to leave this up here in the top left corner to keep a target of what we're actually trying to do here. Now, if we take a look at the various components of the atom and where we could get energy from, we saw that we could focus on electrons, or now we could focus on nucleons, aka protons and neutrons. And the energy by the complete release of an electron, or the energy needed to force an electron to gel with the atom, we would need to have some sort of ionization energy. And that ionization energy we saw could be calculated if we were dealing with photons as something to do with this equation. Now, the nucleons are also bound very, very tightly in the strong nuclear force, and these nucleons, when they're released, or in order to release them, will require what we refer to as binding energy. And this binding energy is what we would describe in this equation. And so what we're going to see here in this video is how can you actually calculate the binding energy, and why does it have something to do with the mass? Another thing we'll notice is that the binding energy of nucleons is much greater than the electron ionization energy, although some of those can be pretty large too. So if I take a look at my intact nucleus, I'm going to describe that as m sub nuc. And if I mass this, I would see that I actually have a smaller value of mass than if I massed each individual part of that nucleus and added all the parts together. So that would be like saying the mass of a car as an intact car is less than if you took the car apart, massed each of its pieces, and added them all together. And that is kind of weird. So let's see what is actually happening here. First, let us write a description of this collection of nucleons. So in order to show the mass of these separated nucleons, I'm going to say the mass of a proton times the number of protons, which we said is the atomic number, Z. I'm then going to add that to the mass of a neutron times the number of neutrons. Now remember, we have isotopes, and some of the number of neutrons are not going to be the same as the number of protons. So what we have to do is take the mass number and subtract the atomic number from that. So we need to do A minus Z times the mass of a neutron. Now what we see is that the difference in the mass from when the whole thing's intact to when the whole thing is separated is actually equal to number of protons times the mass of proton plus the number of neutrons, A minus Z, times the mass of a neutron, minus the mass of the nucleus. This difference, which is known as the mass defect, which you can kind of think of as the deficit of mass, the difference between the two, that is actually going to relate to the amount of energy that is going to be released in this process when you force nucleons together or when they naturally come together. This would be the form of an exothermic reaction. So if I take this mass defect number, delta M, and I divide it by c squared, what I would see is, multiplied by c squared, what I would see is that that is actually the amount of energy that is released when you separate this nucleus. And in most cases, this is a very large amount of energy. Now, because we have this energy mass thing going on here, we're no longer just going to refer to mass conservation or energy conservation separately, but now we're going to refer to mass energy conservation. And what we're going to do in the remainder of this video is take a look at how we can actually make some calculations here to figure out how much energy can be released by splitting up a nucleus, and how that compares to some of the ionization energies that we were looking at before. So in order to do that, we're going to use an example here, and I'm going to be using the example of deuteron, which is really just heavy hydrogen, which is what I've been using as an example in all my previous videos in the atomic physics area. And that is hydrogen that has one proton and one neutron. And so what we're going to do here is we're going to see that the mass of deuteron is 3.34359 times 10 to the negative 27th kilograms. However, because we're using energy now as well, we can also write this as an energy style value rather than a kilogram style value. So what I'm going to do here is write this as 1875.61 mega electron volts, which is the energy unit, over c squared. So this allows me to add masses, so to speak, in the energy form, which is E over c squared, rather than just the kilograms. Even though all of this is going to be a lot of writing, it will allow us to see how much energy can be left. But in order to make it a little bit simpler, what we're going to do is use unified atomic mass units. And what that is was that they took carbon-12, and this carbon-12 has 12 nucleons, and they said that if we divide the total mass of the carbon-12 by 12, we should get the mass per nucleon, essentially, of the atom. Now, it's also going to include some extra things with it, but what we can do then is compare many different masses of different elements together, and then we can take a look at their relative stabilities. So over here we have a graph of the binding energy per nucleon in mega electron volts versus the mass number. So as the molecules get, or as the atoms, get larger and larger, we kind of see that there's this optimal binding energy to make this most stable nucleus is going to be the iron 56 nucleus right here. Now what we will end up seeing is that much larger nuclei, like uranium 235, 238, all these up here, they're going to tend to go through nuclear fission and kind of move in the direction of going to being the more stable nucleus. Other smaller atoms and nuclei are going to undergo fusion to kind of move more towards the iron. And so this is the golden spot, if you will, where everything is combined. So when we want to look and compare different units, if we take carbon-12 as our standard, we can say that one atomic mass unit is equal to a 12th of the mass of the carbon nucleus. And so what we can say then is that if we're trying to find the mass defect for the deuteron, we can say the mass of a proton plus the mass of a neutron, which is all that the hydrogen, heavy hydrogen is made of, minus the total mass of the deuteron. What we find is the following. So I'm going to put this in the mega electron volt per c squared unit, 938.28 mega electron volts per c squared. This is the mass of the proton plus the mass of the neutron, which is slightly different. And I'm going to subtract out the deuteron mass, which I told before was 1875.61 mega electron volts per c squared. And what I end up finding is that the mass defect for that is 2.24 mega electron volts per c squared. The binding energy of the deuteron is therefore going to be that value times c squared, which is going to be 2.24 mega electron volts. And so you can see now why we just leave c squared as part of our unit here, so that we can make the final relation easier to solve. So what does this mean? So this means that over 2 million electron volts are needed to break apart a deuteron into a proton and a neutron. This is huge, and it indicates the great strength of the nuclear force. So if you look at the greatest amount of energy required to free an electron bound to a hydrogen atom, what we find is that's only about 10 electron volts. So this is double, and this is just when we have one proton and one neutron. Now imagine if we had a lot more of those and the reaction that could take place. So this is a very big value, relatively speaking, if we think about how this is just one atom's release of energy. Now that's not a very huge number relative to the energy our cars use and so on and so forth, but that's just one atom, which is a tiny piece of the big picture. So if we think about this a little bit more, what we can find then is that in very tightly bound nuclei, like a helium nucleus, which is known as an alpha particle, we can find that the amount of energy per nucleon is about 7.07 mega electron volts. This is massive, and this is where all the energy comes from in nuclear reactions, which we're going to take a look at in the next few videos.